Feedback topologies, voltage feedback. This topology samples the output voltage and returns the feedback signal as a voltage. Following the conceptual illustrations of figures, we note that the feedback network is connected in parallel with the output and in series with the input port. Figure an ideal feedback network in this case has bits, finite input impedance and zero output. Figure voltage feedback impedance because it senses the voltage and generates a voltage. We can therefore write Vf equal to beta V out, V equal to Vin minus Vf equal to A naught Vin minus beta V out, and hence V out by Vn equal to A naught by 1 plus beta A naught. We recognize that at beta A naught is the loop gain and the overall gain has dropped by 1 plus beta A naught. Note that there are both A naught and beta. A naught and beta are dimensionless quantities. As simple example, voltage feedback. Suppose we employ a differential voltage amplifier with single-ended output as the feed-forward amplifier and a resistive divider as the feedback network. Figure A. The divider senses the output voltage, producing a fraction thereof as the feedback signal Vf. Feedback signal Vf. Following the block diagram of figure, we place Vf in series and the input of amplifier to perform subtraction of voltages. Figure. Here you can see the figures. A. Amplifier with output sensed by a resistive divider. B. Voltage feedback amplifier. How does voltage feedback modify? How does voltage feedback modify the input and output impedances? Let us first consider the output impedance. Recall that a negative feedback system attempts to make the output an accurate replica of the input. Now suppose, as shown in figure, we load the output by a resistor, gradually decreasing its value while in the open loop configuration. The figure effect of voltage feedback on output resistance. Output would simply drop in proportion to RL by RL plus R out in the feedback system. R out is maintained as a reasonable replica of Vn even though RL decreases. That is so long as the loop gain remains much greater than unity V out by Vn, similar to 1 by beta, regardless of the value of RL. From another point of view, since the circuit stabilizes the output voltage amplitude despite load variations, it behaves as a voltage source, thus exhibiting a low output impedance. This property fundamentally originates from the gain desensitization provided by feedback. In order to formally prove that voltage feedback lowers the output impedance, we consider the simple model in figure where R out represents the output impedance of the feed forward amplifier, setting the input to 0 and applying a voltage at the output. We write Vf is equals to beta Vx, V equal to minus beta Vx, Vm equal to minus beta A naught Vx, and hence Ix equal to Vx minus beta A naught Vx by R out. If the current drawn by the feedback network is neglected, if it follows that Vx by Ix equal to R out by 1 plus beta A naught. Here you can see the figure calculation of output resistance of a voltage feedback circuit. Thus the output impedance and the gain are lowered by the same factor in the circuit of figure B. For example, the output impedance is lowered by 1 plus A naught R2 by R1 plus R2 by A naught R2 by R1 plus R2. Voltage feedback also modifies input impedance. Comparing the configuration in figure, we note that the input impedance of the feed-forward amplifier sustains the entire voltage in figure A, but only a fraction of Vn in figure B. As a result, the current drawn in Rn and the feedback topology is less than that in the open loop system, suggesting that the returning voltage quantity to the input increases the input impedance. The foregoing observation can be confirmed analytically with the aid of figure. Since V equal to Ix Rn and Vf equal to beta A naught Ix Rn, we have V equal to Vx minus Vf equal to Vx minus beta A naught Ix Rn. Thus Ix Rn equal to Vx minus beta A naught Ix Rn and Vx by Rx equal to Rn into 1 plus beta A naught. Here you can see the figure effect of voltage feedback on input resistance. Figure calculation of input impedance of a voltage feedback circuit. The input impedance therefore increases by the ubiquitous factor 1 plus beta A naught, bringing the circuit closer to an ideal voltage amplifier. Here you can see the figure, thereby lowering gate source voltage of M1 and yielding a change in VGS1 that is less than delta V. By contrast, if the gate of M1 are connected to a constant potential, the gate source voltage would change by delta V, resulting in a larger current change. In summary, voltage feedback decreases the output impedance and increases the input impedance, thereby providing useful as a buffer stage that can be interposed between a high impedance source and a low impedance load. Thank you.